a lot about electrons. We're going to take a kind of a little detour today. First, we want to define what is nuclear chemistry, okay? We hear this term all the time, but what does it actually mean? The nucleus of an atom is composed of protons, which are positively charged, and neutrons, which have no charge. What they do have, though, is weight, and this is very, very important from a stability standpoint, okay? So even though atoms are always going to have the same number of protons, there may be a different number of neutrons on the inside. We've talked about this before, and we call them isotopes. You may be thinking, well, if they have no charge, why does it even matter? And again, it's because of the weight, the differences in the weight. Little jokes. There's a lot of good Simpsons jokes that relate to chemistry, I found out. So, you may be familiar with the Hulk. A lot of you who are comic book or Marvel fans will have seen the Hulk before, and most people know that he has famously become the Hulk due to radiation. We're going to talk about that today. Okay, so in a nuclear reaction, the nuclei, remember the center, where the proton and the neutrons are, the nuclei of an unstable isotope gain stability by undergoing changes in the nucleus. This is what makes it a nuclear reaction, okay? Atoms don't like it when things are unstable. They're going to do everything they can to get out of an unstable situation and become stable. They don't like it when they are not stable. Just like I don't like it when things are changing all the time either, right? It's very uncomfortable for the atom as well. We've already talked about this isotopic notation. We use this in chemistry to specify, because not every single atom, we can't assume that they all have the same number of neutrons. So this is just a shorthand way of specifying which isotope specifically we are talking about. So that number right here, the big number, this one, that is the number of protons plus the number of neutrons. That's the entire mass that's added together, okay? This number here is just the protons. The protons will not ever change in an atom. It's what makes that atom, and whatever it is, it's what gives it its specific properties. So hydrogen here, for example, will always have a number 1, but this number could change because the number of neutrons could be different, okay? So like I said, the subscript tells you the atomic number, which is the same thing as protons. The superscript gives you the mass, what I just said, the protons plus the neutrons. This will vary. There's a picture of that. Okay, so let's look at this. We're gonna practice identifying these. So elements, what element is this? You can get your periodic table. This is, I'm gonna look for the C. All right, this is carbon. The mass number is the protons plus the neutrons. That's this one. So the mass is 12. Yep. Come on, pen. Okay, that's the mass, 12. Ooh, carbon. The protons, that is going to be 6, okay? That's not going to change. carbon will always have 6 protons because that's what makes carbon carbon. If it had 7, it wouldn't be carbon anymore, it would be nitrogen. So the protons are always, always, always going to match. It's always going to be 6. The neutrons, that's where you're going to look at that top number, okay, this 12, and you're going to subtract the 6. So 12 minus 6 is, of course, 6. Okay, so I will say one area where students tend to make a mistake is that they'll try and say it's 12. That's not the number of neutrons, that's the total mass. It's the protons plus the neutrons, okay? And then we can see that. And just to go a little bit quicker here, so the first place I would look to quickly identify what any element is to go to this 9 right here. Whoop, not too fast. This 9 will immediately tell you that that is fluorine. Remember, what makes an element a particular element is the number of protons. That is what makes fluorine fluorine. So as soon as I know, I can see in this picture that it has 9 protons, I know immediately this has to be fluorine. Okay, total mass, again, that top left number. And then we just subtract. It kind of reminds me of like old school elementary school, like math, where when you're just learning how to do math, they write the numbers like this, you know, and you subtract like that. I don't know. I always find isotopic notation convenient when I'm trying to figure out the number of protons because I can just subtract. Sometimes the other areas where I see mistakes is that students will reverse the position of these, but just think to yourself, if there was just a 9 on top and the 19 was on the bottom, you can't subtract those, right? Wait, because we can't have a negative number. All right, so again, immediately if you look to this number here on the bottom, that 29, that is going to tell you, hey, this number here, that is what defines the element, okay? So the 29, if I look on my periodic table, I'm going to find, go to atomic number 29. 29, there it is. So I can see right there, that is copper, Cu, that's copper. Okay, so my element is copper. The mass, again, is this number here. It's this one. The mass is the protons plus the neutrons. So that is 63. And I can get the number of neutrons all by themselves by subtracting. So I would subtract to get that number, okay? Which is 34. 63 minus 29 is 34. That's my isotopic notation. Okay, and this I'm just gonna go through quickly because we already did a bunch of examples. Okay, so test yourself. See if you can do it. So let's just say you have it in verbal form. It says you need to write out an isotopic notation for an atom that we know has 15 protons and 16 neutrons. Okay, so before I do anything else, I think it's important to remember that we want to look at that protons first, because the protons are what defines the element. Okay, so first thing I'm going to do is get my periodic table out, and I'm going to look for number 15, because once I know that, I know what atom I'm dealing with. So we look, you can see that is P, which is phosphorus. So I am going to start by just putting the little 15 there. I'm going to draw my P. Okay, and now I need to add the protons, okay, the protons and the neutrons together to get the number on top. So 15 plus 16 is 31. So, whoa, why did those connect? 31. Okay, so there's the unsloppy version of that. Easy. All right, same thing. Start with your protons, okay? Find the number 67 on the periodic table. I'm going to find it, and that's how I'm going to know for sure what I'm dealing with. Just go use your periodic table and follow along. Sometimes be aware that a lot of the elements, especially that we're going to deal with in this unit, are going to be on the bottom, because some of the nuclear things are in the lanthanide and actinide series, which is always on the bottom. So if you are like, hey, why did this go from number, example, 57, and then I skipped all the way over to 72, it's just because they're on the bottom. So in this case, 67 is down here. You're going to find it down here. It is HO. So it's got HO, 67, and then I just need to add these up. 95 plus 67, and that'll give me 162. And we'll go a little faster this time. 31 protons. I'm going to find the number 31. There it is. It's gallium. Gallium. So the 31 came from the periodic table again. Just look there, and then I wrote the symbol, and then I just added these two numbers together. This is just a little bit of vocabulary, just so you know what we're talking about. And we're going to discuss her a little later on. But Madame Curie discovered the whole concept of radiation and radioisotopes. She did a lot of work on that. What does that mean exactly? All right. Radioisotope. This is an isotope that has an unstable nucleus. This can be caused by two things primarily, being too heavy or too light. These are problems. It's like Goldilocks and Three Bears. They don't want it too big, too little. It has to be just right. Same thing with atoms. Okay, so a radioisotope is unstable because it is too heavy or too light. Radiation is the energy that is released by a nuclear charge. So we are going to talk a little more about that. Okay. So what exactly makes a nucleus unstable? Well, like I said, I think neutrons don't get enough credit because everyone's like, oh, these are boring, they have no charge. Actually, they are very interesting. They might not have charge, but they do have weight. Neutrons have weight, so they make everything stick together there in the center. The nucleus of an element will become unstable if there aren't enough neutrons, or if they are too many. Like I said, if there are not enough, the atom will be too light. If there are way too many, the atom will be too heavy. Both of these cause a big problem for an atom. Okay, a stable nucleus is dependent upon the proportion of neutrons to protons in the nucleus. It has to be Goldilocks and Three Bears, just right. Okay, it needs to be just the right amount of weight. Not too big, not too small. So, once again, the stable nucleus is dependent on that just right proportion. This chart is kind of funny because it shows that the stable ones are red, and traditionally we think of like red as being like stop, no, bad, but it's a little reversed here. The unstable ones are in the green. So there's a very narrow range where atoms are stable. It is usually, but not always, pretty close to a 1-to-1, like for every 1 proton, there'll be approximately 1 neutron. You can see that here. So when you start getting way more neutrons than that 1-to-1 ratio, it's pretty clear that that is not a stable situation, right? So that's kind of what this is trying to show you here. This is what we're going to use to determine if the isotope is stable or unstable. So on your screen, it's reversed from the last one. When it's in a stable range, it will exist and not be radioactive. So it'll be in this green. If it's unstable, it'll be in this yellow section. This line is really something that I don't want y'all to focus on too much because it's not really going to help you. But what it's really saying is it's showing where the 1-to-1 ratio is. So the protons and the neutrons, when they're at a 1-to-1 ratio, you're not really going to need that very much to solve these. Don't focus on that. I think it will just confuse you. I've noticed that this line usually causes students to be more confused than anything else. So please don't focus on that line. You want to be focusing in on here. So if you plot a point that's outside of the lines, let's say you plot a point and it's like way out here. Whoop. Wow, we're moving forward here. Okay. You plot your line and it's way out here, and then it couldn't exist at all. So let's do an example of this. Okay, so it says an isotope of neon has 10 protons and 16 neutrons. Is this likely to be stable or a radioisotope? So if it's stable, it will be in the green section. If it's unstable, it'll be in the yellow. If it can't exist at all, it will be in the white. So what do I need to do? This is actually really easy. Like even an elementary school student could do this. It just seems fancier and harder because we have terms about isotopes and radioisotopes. It sounds fancy, but it's easy, I promise. It has 10 protons. So like old school, elementary school graphing skills, that's it. We're gonna look and find protons. It is on the y-axis, okay? So we've got 10 protons, okay? So over here, and 16 neutrons. 16 neutrons. Neutrons is on the x-axis. So if this is going by tens, which it is, so this would be 10, and it's got 16, so this would be 15, 16, approximately, right? So if I plot that point, it looks like that would be unstable because it's in, if you plot that out, it's going to be in the yellow section. It's not in the green. So I'm going to say B. It's a radioisotope. Okay, how about if we have it in isotopic notation? No problem. An isotope of 90 yttrium, 9039 yttrium is likely to be, it's lunchtime, is likely to be stable or a radioisotope. So first, do not make the mistake that I see students making sometimes where they try and do something with this 90. Remember, that is your mass. You need to subtract in order to get the neutrons. We need to subtract. So we're going to say 90 minus 39. Okay, 90 minus 39 in order to get the number of neutrons. And I'm going to plug in my sorry, I had to plug in my battery here. Okay, so back to what we were saying. This one, you're going to look at that 90 minus 39. That is 51. Okay, that is the number of my neutrons. I don't want to say that it has 90 neutrons because that's not true. Okay, so here's 50, right? So 51 is going to be like, I'm not going to be able to draw this straight on a computer, I don't think, but we're going to try. This is easier to show in person. So we want to go up in here. That's about 51. And then we've got 39 protons. So that's going to be about right here. And I would say that's it's really close. It's really close, but I would say I'm going to call this one stable because I think this plot is right in there on the green. So I would say this one is stable. That's stable. Okay, and this one has the element protactinium has 91 protons. Could stable isotopes exist? So 91, once again, 91. And look, one interesting thing is that past around about the point of a little above 80, there are never any stable, nothing, it could, unstable ones could exist. There are no stable formations out here past. Once you get above about 84, 85, it gets pretty hard for these to stay stable. So no, it's never going to be stable no matter what. We can't put any neutrons in there that will ever make it stable. We could maybe make a radioactive isotope, but will never be stable. It's too big. No, it's too big.